Hi, this video is more of a follow-up than it is a proper lecture. It's a follow-up to my video on BILsinθ, which was the force on a current carrying conductor. And as I promised in that video, I'm going to give the derivations of all of the magnetic force laws here, the mathematical derivations. And for the logical sort of derivations of them, you can check out that video, it had them. But anyways, more than just a video on the derivations of magnetic force laws, this is a commentary on the nature of science and the nature of derivations itself. And I'm going to be focusing on physics, but I feel like this sort of nature of derivations is relevant to the other sciences as well. So one thing about derivations in physics, if you're like me, you'll always want to know how different formulae came to be. I mean, how did we just come up with this? Was it based on experiments? Was it based on previous theory? How did we create this law that somehow works almost perfectly, although we do assume a lot of things in physics, like no air resistance in most cases. But anyways, so when we were doing magnetism in class, we derived Bill sine theta using the equation that we already knew, BQV sine theta. But when I asked about how we derive BQV sine theta, my teacher gave the derivation through Bill sine theta. And when I searched up online as well, I found the same sort of cycle of derivation. And I found that this is often the case in physics. I mean, quite often I've tried to find the derivation of something and it ends up being given by something which was apparently found using this thing. So who started this cycle? How can we just, live inside this bubble of knowledge? So it turns out that derivation is a very relative concept, again, as a lot of things are in physics. And derivation depends on the knowledge that you have at the time, right? So if you would have done BQV sine theta first in class, then you would derive Bill sine theta using it. And if you would have done Bill sine theta first, you would have derived BQV sine theta using it. So the derivation depends on what you already know. But often this is not how these formulae actually came to be historically. I mean, historically speaking, the one that came first was actually BQV sine theta from Lorentz and Maxwell's equations. And then we derived Bill sine theta. So in this case, it checks out. We get Bill sine theta from BQV sine theta usually, and that's the order in which it was derived. But in some cases, and quite often actually, it's not the case. For example, when we talk about Kepler's third law, it relates the orbital period of a celestial body to the radius of the orbit. And in this case, when we talk about a celestial body rotating, we often derive this law in class, at least this is how we did it. We derive it using Newton's laws of circular motion, like F is equal to mv square upon r. But if you see historically, Kepler derived this based on his observations around 100 years before Newton was even born. So the derivation for Kepler and the original derivation was quite different to what we do. And therefore my point is that derivation is based on the current knowledge and based on the person who's doing the derivation and what they know. But what I want to talk about today is the sort of historical and objective derivations of certain magnetic force formulas. So let's start with Bill sine theta. This formula came from, as I said, F is equal to BQV sine theta, wherein F is again the force on a charged particle, B is the magnetic field strength, Q is going to be the charge of that particle, V is the velocity of the particle, and of course theta is the angle between the particle's trajectory and the magnetic field. Okay, so there are many ways to derive Bill sine theta from BQV sine theta. So I'll start with the simplest, which is let's consider the situation in which Bill sine theta is usually applied. That is, we have a uniform magnetic field between two magnetic poles that are isolated. Although isolated poles can't actually exist in real life. If you see, you'll always have a magnet with one north pole and one south pole, right? And this is due to Maxwell's second equation. But anyways, assuming that we have these isolated poles, we place a conductor between them, let's say a metallic cylinder like this, quite chunky, and then we connect its two ends to a power supply, in this case a battery, so a current will flow, right? And now let's say that because we're only talking about this length L of the conductor that's inside the magnetic field, so we can simplify this situation. Now the force that's going to be exerted is going to be the sum of all of the forces on the individual electrons that are actually the charge carriers passing through this wire in this in a particular time, right? I mean to say that the positive nuclei inside the metal are not moving, they're stuck in this lattice, so they have no effect because their velocity is zero. But the negative electrons, which are delocalized, they can move, and they are what produce the current, and so they have a certain velocity v known as the drift velocity. So the force on this whole piece of wire here, this length L, is going to be the sum of the forces on all of these individual electrons, right? Because they are the ones which are experiencing the force, nothing else. And so let's talk about one giant electron, okay, say a sort of mother electron, which is passing through this length L in a given time t. Its velocity is going to be the same as the velocity of those individual electrons, right? And so its velocity is going to be given by speed is equal to distance upon time. Distance is capital L and time taken is t. So we know that if we assume that all of these electrons can be represented with this one big electron carrying the sum of all of their charges at the same speed, then we know that the sum of the forces of all of these electrons is going to be the force on this mother electron, correct? So we can write another equation, which is that the charge, right, of this mother electron, so given that current is equal to charge transferred past a point upon the time it takes for it to be transferred, we can rearrange this to give that the charge is equal to the current into the time taken. If I substitute that into the original equation, we'll get F is equal to B into I into T into V, which is the drift velocity of the electrons, sine theta. And we can now substitute the drift velocity equation. We get B into V into T into L upon T sine theta. And so you can see that the t's cancel and we get F is equal to BILsinθ. So I hope I conveyed this clearly, but I understand if you don't really get the point, or like don't really get how we abstracted all those electrons to this one big one. And this actually comes from calculus. So if you're interested, I'll now show how we actually, like, what's the meaning behind this sort of derivation and how it comes about through calculus, which might make more sense if you've done it. But if you haven't done basic differentiation and integration, then you can skip forward and I'll come to the other derivation, another technique which might make more sense. So yeah, coming to the calculus explanation.